Hi, welcome to the next part of Lecture 5 Transient Analysis of CMOS Circuits. And we are starting to, or in the first part, we have established that circuit analysis and deriving solutions from or using current equations is somewhat complicated. And what we will do start with the first method of estimation using the fact that we will remove the NMOS transistor and replace it with an RC circuit. Okay, so these are the kind of things we're going to do here. We will remove the NMOS and PMOS transistors, replace them with an RC circuit, and handling RC is much better and easier than the transistor. Now, of course, it is very hard to estimate the resistance of a transistor. So we'll try to estimate the effective resistance for a transistor and use it in our analysis. And yes, very difficult to do so, but you know, you can get a very rough estimate of the effective analysis if you do some kind of simulation, and at the end you can get an average value of the resistance across the transistor, because the transistor is nonlinear, and if you want to replace it with a resistor which has a fixed value, it is kind of hard. So that's why you want to have an average value, okay, for this transistor. It will not be too accurate. Okay, if you want too accurate, then you have to go for simulations. Okay, so the idea is replace the transistor with an RC circuit. So before we go there, let's let me do this, probably easier. Okay, so let's see how we can do this. I'll took the drawing into the whiteboard here and see how we can basically achieve this. So here is my NMOS transistor. Okay, and here there is a K here. What is K here? So this is the NMOS transistor, and there is a K. Well, K is the W over L, the width of the transistor over the length of the transistor. And notice here in this transistor, we want to take it out and replace a RC circuit. What makes this a little bit difficult is that we can look at this transistor from three directions. We can look at it from the gate, we can look at it from the source, from the drain, and we can look at it from the source. These are the three directions that I can look into this device, and we have to make sure that I model this device from all these directions. So if I look at this device from the gate, what I will see the gate capacitance, and the gate capacitance is assumed to be C and times K. Why multiplied K? Because we assume that an NMOS device with a size of 1 will have a gate capacitance of a C. So if you size up this NMOS transistor with a K, you have to multiply this gate capacitance by K. Now, let's take a look at the NMOS transistor from the drain or the source. If the device is turned on, I will see a resistor, and then I will see the diffusion capacitance of the drain and the diffusion capacitance of the source. Recall what we have studied those. Notice that there is no connection between the gate and the source and the drain, because from what we have studied before, there is no current that goes from the drain to the source, or to the from the gate to the source, or from the gate to the drain, and thereby there is an isolation here. Okay, I must admit that we talked about leakage current, but you know that is tiny current. We are ignoring that for a second. Now, so if I look at the source, I'm going to see this R. What is R? It is the resistance of the channel. And when the channel size is 1, I'm assuming the resistance, that is the average resistance. And it is not easy to be computed. This goes through many simulations, and we have to determine this average R. Okay, what happens if my device is not size of 1, rather K? Then, which means that we are increasing the width, all right? Not by 1. So here, 1 is W over L equals 1. But what if W over L equals K, like 2 or 3? When we increase W over L, we reduce resistance, and therefore the effective resistance of the device becomes R divided by K. Now, how about the diffusion capacitance? The diffusion capacitance increases with the size of W over L. So when you increase W over K, the diffusion capacitances increase. So we are assuming that the diffusion capacitance of this unit transistor is C for both the source and the drain. So this diffusion capacitance increases by K for the diffusion of the drain and the diffusion of the source. Now, similarly, we can do the same estimation for the PMOS. Everything is the same. So we assume that the size is K. So we have K capacitance for the drain, K capacitance for the source, K capacitance for the gate. But in terms of the resistance of the PMOS, we assume it is 2R, not R as we have. And the reason is, if I have a unit device with W over L equals 1, right, for the PMOS, the resistance, the average resistance of this equals twice as much that of the average resistance of an NMOS. And I need to unite these R's. So this R is the same as this R. Okay, all right, the same average R here. So I would say that the average resistance for the PMOS is equal to R, and the main reason for that, because the holes are slower, the mobility of the holes is less than the mobility of the electrons, and the holes are the carrier in the PMOS, and the electrons are the carrier in the NMOS, and therefore the holes are mobility, because the holes mobility is 2 to 3 factor less than the NMOS, and you will see that effectively the resistance of the PMOS device increases by 2. And therefore, instead of having an R here, I'm going to put for the PMOS 2R divided by K. Okay, same thing, but except with this little detail. Let's go back to the slides. Okay, so now I can see that I have removed now the NMOS transistor and the PMOS transistor, and I replaced it with an RC network. So let's go and check out. Okay, so what kind of C capacitances here we are talking about? Well, things will range out for the C from 2 femtofarad to 1 femtofarad, for the R from 10K ohm per micro to 1.25 K per micron, and really, these are average values that change per technology. There isn't really that fixed number that we can tell everybody use this or use that. So it's very dependent on the process, and the assignment and the exam. We must give you these values. Okay, now suppose we want now to compute the delay, all right, between across this inverter, meaning I change the input of at A. I want to see the delay when Y changes. And now what we want to do is that you will see that there is a charging that happens through the PMOS, or a discharging that happens through the NMOS. Okay, so the PMOS or the NMOS, and this is now the load. So notice now what I do. I replace the gate load of this second inverter with 2C and C. Okay, why 2C and C? Because the gate capacitance here, right? The gate capacitance for the NMOS is so let's go back slightly here and go to the previous slide, so we remind ourselves what. So remember that we said for the gate capacitance we have KC, K times C. So let's go back to our example, and here for the NMOS K equals 1, for the PMOS K equals 2. Okay, these are two different cases. So now for the gate capacitance that is seen by this device. Okay, oops, I shouldn't use this one for now. So let's delete this. Okay, so for the gate capacitance that is used by this device, it is K times C. Since K equals 2, this becomes 2C. And for this device here, right, for this device, it is K times C. K times C. And K for this NMOS equals 1, so it is equal to C. Now, how about this network here? Well, let me change the color for a second here, and that's the. Okay, so this network here, which is this one here, corresponds to the PMOS. So I take this PMOS and I replace it with this. Notice that here we have 2R. Okay, it is equal to R divided by K, and since K equals 2, right, for this PMOS, the K cancels the 2, and I have. Okay, for this one it is R over K. Since for this MOS the K equals 1, we will get an R. And here we have KC, K equals 1, C, so stays as C, and this is KC, K equals 1, stays as C. Here for the PMOS, K equals 2, 2C for the drain, for the source, 2C for the drain. Now these capacitances shorted by the power supply from these two sides, and this is shorted by the ground, so we ignore them. Okay, I'm left with one of those resistors, either this or this. Let me choose a different color. One of those resistance, either this or this, will be on for charging or discharging. So I have it here, one of them, either this one or this one. Then I add these capacitances, which are this capacitance plus this capacitance plus so you can see them right here, this one here, and this one is here, and then I have this capacitance from the gate. All right, okay, so you can see them right here. Okay, let me probably okay, so let's see, choose a different color here. These two capacitances will come and sit right here. Now we can add all these capacitance, and we will see that this is a network of what? Of an R and 6C. And we established earlier that the delay of such a circuit is what? 6RC. So the delay of the circuit is 6RC. The delay that when I change the input of this inverter to see it at the output, given the load that it is driving one transistor, one inverter, sorry, it is 6RC. So if I tell you on the exam, for example, or the assignment, that R equals 10K ohm and C equals 2 femto farad. Okay, so you multiply by the 2, so times 6, right? So now you can get about what equals 60 or 120 let's see, 120 picosecond. I hope I got that right. 120, because the K reduces the femto to pico, so that is 12, okay, yeah, 120 picosecond. Okay, so whatever values that I use, if I don't give you values in the assignment or the exam, just use the expressions as your final answer. Okay, and now we can okay, so this is saying that if we do spice and we do our RC model, we are getting very close results. Okay, and now if we go for a NAND gate, this structure is a NAND gate, 3-input NAND gate. These are the PMOS, and these are the NMOS, and these are the appropriate sizes for them. We will study this gate in the next in the next chapter. Okay, but for now we'll establish that this is the way the PMOS transistor are connected in parallel and the NMOS connected in series, and these are their appropriate sizes. So if we take the PMOSs and the NMOSs to replace them with the RC circuit, we will get with something like this. It's a bit messy here, but eventually these capacitors shorted with the ground and power, they will be eliminated, and then you will see that for every input, when we look at it, we will see there is a 3C and a 3C capacitance and a 2C capacitance, which is right here. Okay, a 2C. So that's the 5C here. Okay, and for the output here, you will oops, I think I have to the gate capacitance. I should get, yeah, I should 2C. Okay, 2 of the C, and from, okay, so for let's see, so this one here, how about the output here? I've got here are the diffusion capacitances. This goes out, short circuit. This is diffusion capacitance number 1, diffusion capacitance number 2, and here I get from everyone 2C, 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 right? And I get plus this 3C, I get 9C. Okay, now the input capacitance here, this is not the gate though. The input, I should have a gate of 2C plus a gate of 3C. That explains the 5C for every gate here. Okay, because the input, every input sees 3C from the NMOS and 2C from the PMOS. That explains the 5C here. Okay, now, so this is in terms of capacitances, and in terms of when I plug in the RC resistance, notice these NMOS sizes are 3, so I replace them with R over 3, R over 3, R over 3. Notice the PMOSs are of size 2, so I replace them with Rs. Okay, when we do a falling, meaning a discharge, we have to discharge the capacitance like so. So you can see the 9C, it has to discharge like so. But as well, I have to discharge as well these intermediate diffusion capacitances. Okay, so that is for the charge. I have to go through the PMOS and charge this. And sometimes if we want to be accurate, we need to take care of charging also the intermediate diffusion capacitances of the NMOSs. Okay, so because these are need to be charged as well. Okay, now if we need to do this series of charging and estimation, we need to discuss the Elmore model. And the Elmore model, what it says is the following. So suppose you have a long series of RC, RC, RC connected as such. So what's the effective delay of this RC network? And to do it, to have a good estimation, somebody called Elmore provided for us a good delay estimation. Said Elmore the following: first, you have to charge this node, and to charge this node, you need RC1. Then we need to charge this node, and to charge this node, you need, let's just use a different color here. To charge this node, you need R1 plus R2 times C2, the capacitance is this node. Then you need to charge this node. Let's use another color, okay? Which is, let's say, for example, this color. We need to charge this node. So to go through this node, we have to go through R1 plus R2 plus R3 times the capacitances in this node, which is C3. And then you continue apply this process all the way. You add these delays, and this becomes until you get to the last point, and this becomes your delay. Okay, so for example, let's take an example here on the whiteboard. Okay, so let's take an example here. Suppose, for example, you have this network. This is R. Okay, this is a C, and this is R, and this is a C, and this is R, and this is a C. So we want to have the estimation of for how to estimate the delay for this network. And we say the delay for this, the delay equals, first I need to charge this point, which is equal RC plus, then I need to charge this node, which is this one here. So I have to go through two R's, R plus R times this C. Okay, let's see, this is a C, so times C. Then I need to delay, I need to charge this node, which is this one here. Let's see, we have a C here. So this, we have to go through R plus R plus R, as you can see here, times the C. So that becomes our delay. Okay, right? So this is called Elmore delay. That's an estimation for an RC network. So let's go back to our lecture here and say, okay, so this is that. Suppose now, with this in mind, suppose I have a single inverter. Now it is driving not just one M of those inverters. If that is the case, then I'm going to use the same network for this guy here, the first one. But for the gate delay, which is this one, I have to multiply the gate delays by M. And that's why you can see the same RC network we used, except this M popped here. Why? Because this M represents the M gates, which are load on this transistor. After all, what we are trying to do here is that we are measuring the delay of changing the input and changing the output. But the output, unfortunately, has M of those. So we write the equation. We say that the delay is 3 plus 3M times RC. And notice that when M equals 1, right, this equation becomes 3 plus 3RC, which is equal 6RC, which is the same conclusion that I have 1 or 2 slides earlier. Okay, so these we call them an M load of identical unit inverters. And the unit inverters always is an inverter with the PMOS of 2, size 2, and which is W over L equals 2, and for the NMOS, W over L, a size of 1. That is the definition of a unit inverter. Okay, that is the definition of a unit inverter. Okay, now for this NAND gate that I started earlier, now since if I want to charge this node, the output node, I'll have to charge this output node and the intermediate nodes. And if I want to discharge the output node through the NMOS, I have to discharge this first, then this first, then this first, and I come up with this equation. Okay. Okay. With so you can see that these are the delay for the NAND gate. And on the as far as the contamination delay, I'm not covering it in this class, and we'll stop at this point and we'll continue later on. Thank you very much.